The most serious people you're going to get sitting through.
Yes, but how many views do you get on YouTube when you have a really hard Well, I mean, I don't know.
So
the great Donald Knuth once explained that it doesn't matter if it's popular, that doesn't necessarily mean it's right.
okay, we're going to get going though.
Anyway, yeah, enough philosophy.
There's interesting discussion going on there, but okay. So today we're going to continue discussing a topic that we discussed a long time ago in a galaxy that may seem far, far away, and that is coverage testing. We talked actually about, we gave hints as to a couple types of coverage tests and what we see. And today we're going to go to the heart of some of them. So we'll be talking about state-based testing, transition, state-based coverage, transition-based coverage. We're going to see transition pair or tuple coverage very briefly. And then, as time allows, we're going to start to talk about one that's called prime path coverage. Okay. So you'll note that last time this slide could actually go in both courses. We talked last time about how models we articulated simplified representations of it says some entitles, some entities. So an abstract description of some thing that we want to characterize, some thing in the external world often. It may be a thing in the form of a software artifact. And why do we create these models explicitly? Well, because otherwise we're creating them in our head in a way that's inaccessible, that's hard to share, hard to refine, critique, etc., hard to evolve. And by making them explicit, we can reason about them more consistently. And models vary hugely in level of rigor, but even informal models can be very helpful. Now, why am I talking about these models in software development, given that I teach a course in a few hours on modeling using simulation? Well, models play a very important role in software development. In medium and large size software development projects, there's a huge amount of information that you need to reason through and understand its implications, various things. That information can vary from information about the schedule, tasks, for example, that might be incorporated in the schedule, information about high-level design associated with pieces of a program, information about what test cases test what features, sort of information captured in the test matrix, information about how requirements map to test cases, or requirements map to design components, or map to test cases, etc. Or the components of the organization, components of the implementation. So model types can help us organize this sort of information. They're abstractions. They hide a lot of details, but they can capture essential, underlying essentials, regularities, essentially, about what we're characterizing. They can capture the underlying regularities that we need to reason about, rather than being surrounded by a welter of detail at all points. We prefer to be able to think clearly and understand the most important essentials, and models help us do that. So models that we create in the software development process help us think through choices. Those choices may be choices about schedule, there may be choices about our division of testing effort, there may be choices about whether to accept or proposed requirements change, etc. And these models can be very useful for reasoning through the implications. And it turns out that models created for other purposes within our program will be able to help us improve our testing. And I'd like to encourage all of you, when you hand in your final deliverable, and indeed your post-mortem, to see if you can include some models of sorts within your project. Now, we've talked about some components of model-based testing already. So several, I guess maybe 2 weeks ago now, we talked about orthogonal array testing, decision trees, flow graphs, and Boolean, and actually, I may have mentioned, but I didn't go into Boolean decision criteria. We'll come to that. Who can remember for me what an orthogonal array is? define what an orthogonal array is. What is an orthogonal array?
Has to do with
Good. Okay.
Congratulations, you know what orthogonal means.
So what's an orthogonal array?
Is an orthogonal array, doesn't it have the minimum number of test cases for complete coverage, but it tries to avoid overlap, or by definition it avoids overlap?
You're in the right area, but the specifics require refinement.
Yeah.
So if we have a set of choices, each of them associated with some particular criteria of relevance, some particular attribute of relevance. Maybe it's, remember I showed an example where you had a platform like an OS, an operating system.
Right. It doesn't test all pairs, but it ensures that each option within a set of values is tested.
Again, you're in the right area. You're in the right zone. You're not swinging at balls or something like that.
Is it when you don't, or when there's too many inputs to actually test properly, that you try to cover as many as possible?
Okay, yeah. The word proper is a bit loaded, but you have too many possible combinations of values to do exhaustive testing. To do testing of all possible alternatives. So maybe you have, operating system as your first choice, and then you have, web server as your second choice, and then you have the browser on the client side that's used to hit it, and then maybe you have, some other, maybe it's the language in which it's to be displayed, etc. And maybe for each of these you have, 6 different possibilities. Maybe there's a fifth option out there. In which case, how many possible, if you were to test this exhaustively, all possible combinations of these 5 attributes, each of which has, say, 6 choices, how many different combinations are there?
Oh wait, no, it's 6 to the 5.
No, because choosing a specific OS, let's suppose they're orthogonal. So choosing an OS allows you to still install a bunch of different web servers, and choosing a particular web server doesn't rule out browsers, etc. So how many would it be?
6 to the 5.
Okay, 6 to the 5th.
Well, I was going to say, plus.
Orthogonal arrays don't test. So it works upon the premise of having each option within each category selected at least once, and such that
Correct.
each pair is tested.
Exactly.
Yeah,
So every single possible pair between the different columns is tested at least once.
So it's not every combination is not tested. Each pair is tested.
And that's important because, well, why is it important pair? Why do we care? Oh, okay, all pairs are tested. So what?
There might be a bug in this example, there might be a bug on Apache on Windows, but not on
Correct.
Linux.
Right. So an awful lot of our problems come up in one of 2 ways. Either our system just doesn't work at all, on a particular OS. It crashes and burns always on Windows. Or it comes up in a pairwise situation. Because there's a lot of compatibility issues that are fundamentally about A cannot work with B. Now there are some where you have to be A, B, and C together, but those are much rarer. So an orthogonal array tests all possible pairs, and it does so for every given function. So you take every given pair of attributes. So you're guaranteed to examine every possible pair of OS and browser, for example, every possible pair of OS and language, every possible pair of OS and web server, etc. And similarly, web server and browser, and web server and language. All of those pairs are guaranteed to be tested at least once. Now, when you're doing these tests, you're always doing a particular test on some particular value for each and every one of these 5 columns, right? You're always doing it with some particular language, some particular browser, some particular web server, with some particular OS, etc. And that may simultaneously allow you to tick off, so to speak, to satisfy the requirement of testing several particular pairs in that process. So you're going to be simultaneously hitting, for each of your test cases, you're going to be hitting often several pairs that you'll tick off. And it turns out that orthogonal array testing is vastly, I mean, incomparably cheaper than doing all possible combinations of values. Okay. We also talked about, for example, Latin squares, where you're guaranteed to examine each particular value of each particular column at least once. So you're guaranteed to at least have some test that includes, you know, a Red Hat backend, some test that includes a Ubuntu backend, some test that includes a Windows backend, etc. And similarly for web server. It doesn't even guarantee which of those is stronger, which of those actually tests more thoroughly, if we could say it. Orthogonal array, yeah, because it's it's guaranteeing all pairs, not just that each given possible value of each one is tested, but all pairs of them. So orthogonal arrays is quite a bit stronger, but both are ultimately ways of kind of simplifying the testing process in a way that allows you to focus on the things of highest risk. Talk about decision tables or trees that depict different choices, systematically hitting each of those choices. Today we're going to be talking a bunch about flow graphs. This is just a reminder. Okay, so let's talk about coverage. Turns out that there's many notions of coverage we're going to appeal to today. The one we're going to hit in the most detail is path coverage. And we'll be talking about that for the bulk of today's lecture. So that includes state-based coverage, transition coverage, pairs of transitions or tuples of transitions, and prime paths. Okay. We will further talk about constraint-based coverage in a separate lecture. And here we're dealing with logical conditions that need to be tested. And I'll make some comments about code coverage, which often has to do with sort of statement level coverage. So the common theme for all of these coverage procedures are, number one, this is highly this is right for testing final exam. Number one, we first have to identify the set of things we need to cover. Maybe these are nodes in our graph, or statement level coverage, or basic blocks for statement level coverage, or maybe they're individual transitions for transition level coverage. Maybe they are prime paths for prime path coverage. Maybe they are, for example, specific combinations of OS and web server and browser and language, etc. In that case, before. So we identify the set of things we need to cover. Number two, and this is for paths, we develop a set of paths that include all the things we need to cover. These paths need to cover all these things we need to cover. Now, a given path will typically cover multiple of the things we need to cover. So, for example, a given path will cover multiple basic blocks, or it will cover multiple transitions within the underlying graph, or it will cover multiple prime paths. So don't get those confused. We want to cover a certain set of prime paths. We then develop a set of paths that collectively cover these set of things. And given one of these paths may cover multiple, we'll typically cover multiple of these things we want to cover, the prime paths or whatever. And then, in the final step of this, we develop a set of test cases, concrete test cases, things that you can feed into your program that will cover these paths, that will elicit the behavior such that the paths or the appropriate paths are covered that you target. Okay. Now, these test cases may exercise other paths that are not included in the specified paths. That's fine. But you're guaranteeing that you cover this set of paths which collectively cover the set of things you wish to cover. Okay? This is going to follow us through today's lecture. Yes?
Is orthogonal arrays we covered? Because you covered at least.
No, things we need to cover for orthogonal arrays. What are the set of things? They are pairs. Pairs. Now, if we're saying, okay, we developed a set of paths, here we need to develop a set of specific combinations of values across each and every column that will cover all pairs, right? And then test cases, for that, we would be, it's actually close to this, but we would need to specify more information. For example, we need to say, okay, what particular page are we going to hit, for example, for each of these.
Yeah. So see, wouldn't like every time you have a pair, like to cover it in orthogonal arrays, wouldn't that like, I'm thinking of everything like a big color block, and then that would just like knock off the color for each time you did that. So wouldn't the whole, and if every pair is tested, wouldn't that knock off everything? Wouldn't that everything be different colors?
So
each pair is tested, but not each combination is tested.
correct, correct. So we can enumerate all possible combinations of these, right? But a given pair, say a pair of an OS and a web server, will typically appear many, many, many times in that, right? So it's going to be hit off. As long as you hit one of those items, you're going to be able to tick off that as having tested. Does that make sense?
Yeah, for sure.
Okay, so this will be our template that follows us through the components of this lecture. So to give an example, we identify statements in our program, or the basic blocks in our program. We'll develop a set of paths that will cover them. Then we'll develop test cases, very specific input that will exercise those paths, and that will allow us to test all the specific basic blocks. Okay. So why do we create these sort of graph models with paths and so on? Well, they provide the standard of models, clear reasoning about them, clear documentation, communicating what is this set of test cases cover, what's the purpose of it. Allows us to, in some cases, automatically derive test cases against model specifications. So there's a whole set of research associated with automatically using this to formulate test cases. Okay, I think I'm going to skip over that in the interest of time. Suffice it to say that if we have a specification of a system in longhand, we can typically render it into a state diagram like this. So, for example, here we have a longhand specification that specifies the flow of products when they need to be sent in for repair. So, under such and such a condition, if they're covered by warranty and maintenance contract, then you can go through certain procedures to request maintenance, bring in the item to a designated station. If it's requested such and such, the item is then picked up or it's shipped, and you can kind of map this into a set of states. Okay, so we're in the state where no maintenance is needed. You're in the situation where it's waiting for pickup, or where it's at the maintenance station, or you have a situation where the object is recognized as requiring maintenance, but there's no warranty, so it's waiting for approval at the station as to whether it will be repaired, etc. So these are a set of states. Similarly, if we have a specification of sort of process shipping, we can map it to a flowchart, sort of like this, which specifies the set of different processes that are required to handle a shipment, reasoning about a shipment, okay, processing a shipment order. So, this is the process of abstraction. We're hiding certain details in the background here, but we're capturing the essentials of the flow in a fashion that allows us to get greater clarity about what the steps are and how they relate. This information is all present within this closer description. Often there's even more detail here. So this is the abstraction process that gives us this. Now, once we have this formulated in a situation where we have these nodes and we have these transitions, then we can apply the sort of algorithms that we're going to be talking about today. Okay. Now, it turns out that there's the abstraction process ignores details by design. That's almost how it's defined. So certain types of information will be suppressed. So for example, if we have a situation, be suppressed or it'll be expressed with annotation. So here, for example, we have a situation where something is been requested for repair, and there's going to be a set of processes that will play out, that each of which could involve waiting for the component to be received, the component to repair it. So for example, maybe you have a snowblower and you need a replacement for, you know, the gas head cap or something like that. Or maybe you have a printer and you need to replace one of the buttons which is not working properly, and they have to send that away. Well, it turns out, regardless of whether repair is done at the maintenance station or the regional headquarters or the main headquarters, in all cases they may need to wait for the component. In this case, what the authors of this diagram did is they essentially violated one of the typical rules of these sort of diagrams by showing a history-dependent state. Okay? So if you're dealing with a maintenance station and you lack the component, you go to the wait for component state, but then when it arrives, you go back to that state. Similarly, if you're in the main headquarters and you lack a component, you go and you request that component, you wait for it, and then it arrives, you go back to this headquarters. The thing that's violated here is that this state needs to kind of remember the state, the previous state, where it came from, which these other states don't have to. So here we've introduced a richer semantics or annotation into this, to this diagram to reason about this. Traditionally, these states are memoryless in the sense that you don't have to remember from what edge you came in to determine which edge you go out. But this is an example of sort of information that may get packed into a diagram like this. And here what we've done is essentially tried to omit the need to show 3 different versions of this wait for component. Yeah.
So for state diagrams, going back to the finite state automaton analogy, they should essentially attempt to avoid being pushed down automaton as much as possible.
That's correct.
Okay.
That's correct. I mean, let me put it this way. A push-down automata is a perfectly fine abstraction of things. It's a nice model for things. But it's normally more complex than is used in a lot of documentation. So if you want to specify this can be implemented as a push-down automaton, and you have explicit semantics for where the pushes and pops occur. That's perfectly fine. It's just typically the mechanisms to process it automatically, for example, to derive test cases would be more complex. Okay, a PDA is provably more powerful than a finite state machine without a stack on it. It can accept a context-free grammar compared to accepting a regular expression. Yeah. Okay, so what we're going to be doing here is working through a mechanism that will let you derive legal paths from a program from start to finish. Start at the entry point of the program, and you're going to have to go through to the finish. That's what your test cases will be doing, where it will exercise the desired level of functionality, hitting all states, hitting all transitions, hitting a distinct set of paths. Okay. And then we're going to find test cases, specific test cases that will exercise these paths. Now, it turns out there's a variety of ways to do it. And I showed this slide last time. And this slide is sort of Ammann and Offutt's book, really excellent book on testing, Introduction to Software Testing. So we're going to start with node coverage, what I call state coverage in that previous slide. And we're going to then talk about edge coverage. We'll mention a little bit about edge pair coverage, and then we'll talk about prime path coverage. However, it turns out there's a variety of ways to construct a hierarchy here. And this is what's called a subsumption hierarchy. Does anyone know what that means? What do I mean by a subsumption hierarchy? Okay.
The further you go up, it covers everything beneath.
Right. Yeah. So edge coverage will subsume node coverage. So if you achieve edge coverage here, will actually be guaranteed to have secured node coverage for within the rules for what counts as a proper problem. If you have edge coverage, you automatically have node coverage. If you have edge pair coverage, you have edge coverage. If you have prime path coverage, you cover all edges. However, this is not a strict linear hierarchy. What I mean by that is that, for example, complete round trip coverage, which I think I mentioned in one or two slides at one point, is neither subsumed by nor subsumes edge pair coverage. So if you have edge pair coverage, guarantee you've tested all pairs of edges coming into a node and going out, coming in this way, going out that way, coming in this way, going out that way, coming in this other way, going out, etc. If we cover all that, we're still not guaranteed to have complete coverage or round trip through loops, and vice versa. Okay, so turns out this this hierarchy is not a complete ordering; it's a partial ordering. But generally, going up, we have more complete coverage. Now, let me ask about this one at the top: complete path coverage. Do you think that's feasible?
Why do we need it for any reasonable software project? No, because that means we have to say, try to do complete path coverage on the Windows kernel. There's millions of lines of code in there. That's complete path coverage may not be is not only infeasible in terms of the amount of energy required to do it. Sometimes you can't fake those errors. Like there might be a weird border case that you can't really simulate.
Mm-hmm. Moreover, if we think about what complete path coverage is going to mean, what it means is if you have a loop, if I have a loop, so here's a while loop based on some condition, and there's some code in it. What would complete path coverage mean? If I want to cover this completely, all possible paths through this program, even through this one sort of fragment of code, what would this involve? All possible ways that I could go through it. So call this block A above it, block B below it. What would be one path through this program?
The while loop, the body of the while loop is never executed.
Good. And maybe we'll call the body of the while loop C, right? So one path is AB by itself, right? We never execute the body. What's another path? ACB. How about another path? Yeah, okay. AC to the NB. So suppose this is now, instead of just being while, suppose it's while true. Could you have that? Do we have programs which have loops which
Yes.
yes, like a shell of an operating
the Linux
system?
kernel has many infinite for loops.
Yes, exactly. Exactly. So there's no shortage of programs these days which are designed to run as long as possible, subject to user input, to disrupt them. And in general, this could run arbitrarily long. We could iterate through this loop as long as it's long, until the cows come home and beyond. So exercising full path coverage here is not going to be feasible within any finite time.
Is this somehow very subtly linked to the Vulkan?
Yes, it is.
Okay.
So I was just about to get to Logan's next question, which is why does it matter? Why do we want full path coverage? If I told you, man, I've been doing research. I found a way to, through quantum computing and time travel, I found a way to do complete path coverage. Would that be a good thing for computer science? If I had a practical way to do that, I mean, it's ludicrous, but if I had a practical way, would that be a good thing?
No, it would mean everything up until this point is complete bottlenecks, basically.
Okay. But if I am unable to achieve complete path coverage, are there vulnerabilities that might lie hidden still? Might complete path coverage be needed if I wanted to fully expose certain vulnerabilities? Yes. And why is that? Well, for example, there could be a memory leak here that can occur arbitrarily far into it, would eventually be revealed. There's some magic way I could perform complete path coverage. It might reveal some defects that wouldn't be revealed through prime path coverage, for example. That wouldn't be revealed by merely 100 iterations up to 100 iterations of this loop. That 101st iteration could contain a real problem in the form of an out of memory error or something like that. So while this would be ideal to achieve complete coverage through all possible paths through that program, it's normally impossible, and unfortunately that has consequences. It exposes us to vulnerabilities. So we try to do a good job with what is feasible to do. We try to marshal our limited resources, our limited time, to test things that reasonably exercise the program reasonably well. And prime path coverage is going to be the highest one within this diagram, within the exercise. Okay. Complete path coverage is not possible. If we could solve complete path coverage, we could solve the halting problem. We could determine if a program is going to halt or not. We could figure out, okay, how many iterations of the loop does it require to finish? If we could do that in some finite time, we could determine if it's going to halt or not. And it turns out that that's logically impossible to do. It has to do with Gödel's incompleteness theorem, and it's provably not possible. So complete path coverage is simply not a feasible goal. It is logically inconsistent to imagine achieving that. Okay. So we have these different levels of path coverage. Let's talk about the first of them, state coverage. So with state coverage, we are attempting to hit all states. And you remember this diagram I showed you before with states associated with airline ticketing. And in general, it'll handle a wide variety of consumer cases as well. So situations where we make a reservation and we cancel before paying, situations where we make the reservation and then we pay for it, but then it gets canceled, situations where it's made for and paid for and actually it's formally ticketed and then canceled, or it's ultimately used. And if we wanted to achieve state coverage here, we could do so by hitting all states. And how do we do that? Well, to do that, remember, we can't just say, well, I just hit each of these states. We have to define paths that will hit these states. So to get to this state here, canceled, non-paid, following making the reservation, but nothing more, we'd have to go to the made state and then the cancellation state. This is a path that we would need to realize through some test case to be confident that this canceled non-pay state works. We can't just magically appear here. We have to somehow get here through a legitimate path. Similarly, this case where the ticket's actually used, we need to go through the requisite set of states that will verify that's working properly. Similarly for cancellation following payment. So this is state coverage for this simple example. Does this simple example cover all edges? Are all transitions covered? Certainly this one is. This one here. Are all of them covered? Why not? That's true, because our focus is the state. So we can get to this cancellation by customer state defined here in common if we've made the reservation and then cancel it, or we can get to it through payment and then cancel it. It's the same underlying logic that apparently is in place here. And so we only end up testing it one way. We're shooting for a lower bar here. We're not aiming to cover all transitions. Okay? So does that make sense for state coverage? On that state coverage? Okay. Here's this other case that we were looking at. So here we have two test cases. You'll notice, ladies and gentlemen, and this is something where it's almost desk-poundingly important. I want to emphasize again, and it seems like I never emphasize it enough, these test cases need to start at a legal starting point and finish at a legal finishing point. So here, we need to start these paths at the initial state that we start at, and then they need to go through a set of legal state transitions and finish up at a legal state. So here, we are starting out this no maintenance state, and that's in fact where we're ending up. And there's two routes we could take, two paths we could take through this that would hit all possible states. So the first of them might be testing our system with a case where we have no warranty in place. It awaits acceptance because of that to estimate. So they estimate the cost. They wait for user acceptance of those costs. If that is then rejected, then it's returned to the no maintenance state. So it just goes back and returns. That's one path through this. They'll exercise those states. These other states could be exercised by a different path. So you've requested, as a US or EU resident, this thing, it's waiting for pickup. It goes to a repair station. They end up needing to delegate it to a regional headquarters because it's too complex to repair. Then they go and they request a component to fix in this thing. It goes back to the regional headquarters. It needs to be repaired in the main headquarters. It goes into a repaired state, and it goes back to this no maintenance state. These are two paths that collectively exercise all possible states of this diagram. Okay, basic advantages. Hey, essential functionality is exercised here. At least you're going to all states. You couldn't really pass the red face test on something like this if you hadn't tested out a situation, for example, where someone rejected the amount it was going to cost. They said, no way, it's way too expensive for me to get it repaired or send it back. If you hadn't tested that your system functions in that situation, you can't plausibly claim you've exercised it well. So this tests all those states. That's great. That's a good start. On the other hand, there's a huge number of cases that are not tested. An example would be workflow for non-US or European Union residents, or cases where residents are performed but not routed through the headquarters. We only tested it when it was routed through, in fact, the main headquarters. Or cases where it's dropped off at the maintenance station directly, for example, requested here. We haven't really tested those cases, those transitions. So we've done some face validity checks, but we haven't thoroughly tested it. So this is the simplest. It's also the weakest form of coverage. And I would tell you, folks, that when you run most coverage tools, this is the sort of testing done in your program. So when it says 98% coverage, it's 98% of hitting components of your program. What is missing here? How you get to those components. And often coding defects are found there. So, for example, code in this block might work fine for one path through the code, but it fails on another path. So, maybe on one path through the code earlier, there's an uninitialized pointer or a reference, and when it hits this point, it blows up, whereas another path is just fine. You're not thoroughly testing the different ways you could get to this point, so you only see the one that was successful. There's a lot of cases where, for example, the if statement, if the body of the if statement is hit, it works fine. If you go to the else case, things will cause trouble down the road. So the next higher level of coverage testing is transition testing. So here we're doing edge-based testing on these tracks. So here we're exercising all transitions at least once within the program. Now, we're going to have these test paths defined. Remember, we first have to dictate what is it we're trying to find. Well, here we're trying to find all transitions. We're trying to cover all transitions. Find is not the right word. Cover all transitions. Okay. Before we were doing that starting point and finish at a legitimate finish point. A given test path may cover many edges. It typically covers many, many edges. Just as before, when we were with the, well, we could do it, show it with this one. These two, you know, this test path, it's shown in red, covers all of these different states. You know, this case here, case number 1, covers all of these 4 states, right? So similarly, for a transition case, a given test path will cover many particular edges. Now, for each path, we're going to have to find a specific situation that will exercise that path. And actually, specifically, we're going to find test cases that are going to cover all our paths. Like particular inputs that are going to exercise those paths. Okay. And you'll notice sometimes we may have to deal with the abstraction that we've used. Sometimes there may be paths that we'd like to check, but we actually can't. We can't exercise them because they're logically impossible. We'll see a situation like that, I believe, in the slides ahead. So in other words, you have to remember, you're dealing here with an abstraction. You're dealing with abstractions, the underlying situation, and you may say, I want to take this path, and when you really study the details of it, it's not possible, because the abstraction didn't capture those dependencies, in which case you have to identify another path that covers all the underlying transitions. Okay? So here we're exercising all transitions at least once. We want a set of test paths that will exercise all transitions at least once collectively. Collectively test all transitions at least once, and then we'll find specific test cases that will exercise those paths. Okay. So let's go through this. Okay, so here's transition coverage for that earlier diagram. Here we're going to test these specific transitions, not just the underlying states. We're going to get a lot more coverage than the underlying states. Are we testing here all the underlying states? Yes. But we're further doing testing on things that were previously ignored. For example, this transition here, or this one here, from paid to canceled, or from ticketed to canceled. Okay. So here we have to cover the transitions between states and blocks. What are the testing gaps here? Well, one of them is we haven't covered combinations of conditions. So, for example, in this transition here, if we have an if statement down here, we have some things within the if statement. We will test, for example, if this if hits its block or goes the other way, right? So if we have an if statement, I'll write it on the board here. If we have if, let's say if bar is true, then A and then B. If I just wanted state coverage, what would be sufficient to test this? Okay, bar is true and false. Oh, excuse me. If I wanted state coverage, what would be enough to test this? Just having bar true is enough, right? I've tested all of these guys, and I've tested all of these guys. That's enough, right? You see that? Okay. If I want transition coverage, what do I have to do? Yeah. So I mean, we can represent this as a graph here. Maybe it would be simpler if I represent it as a graph. Here we have the if, and this is A, otherwise B. So with state coverage, we would get state coverage just by going like that. If I want transition coverage, I need to do what also? Yeah, like that. So for state coverage, just that. For transition coverage, I would need to have a B, but I would also need to just do B and not A, essentially B by itself. So in other words, fall through. So I need to do both those transitions. Now, that's great. We tested that. But what we haven't tested is combinations. So suppose, for example, earlier on, you had a different if statement. So, you know, you had an if which depended maybe on a different conditional, and you had something like this. Here, if we have a situation like this, it's not guaranteed that we examine all possible ways we got to this point in combination with all possible ways to leave this. So, for example, maybe we'll call this guy C here. And I'll put, just for clarity, oh man, I'll put a D above here. Okay, this is, no wonder I didn't go into art. Okay, so we could test this thing using transition coverage alone. So let's go through this. For if this is D and this is C, and this is A and this is B, and let's give this guy a name here. Okay, E. We'll just give that node a name. Sure. Oh man. Okay. This is gonna get. I'm gonna redo this. So this goes with this example. These guys I'm going to name. I'm going to rename these for clarity. And in fact, I'm going to redraw that.
Just redraw the whole thing, maybe.
Okay, I'll go redraw it over there. Let's redraw it over on this side. Okay, so we have an if statement up at the top, and for clarity, we'll give this a name because it's part of the basic block. We'll call it A, and then it has a B, and then come down here to a C. This is further an if statement, though based on a different condition, right? And this is C, and then we have D here, and then we have an E, and we have those transitions. Okay, so give me statement coverage. What would be a transition path that would be adequate for statement coverage here? Speak, use.
True, true.
Sorry?
True, true.
Okay, true, true. So give me the path through the node name. A, B, C, D, E. So statement coverage would be covered by that path from start to finish here, right? Okay, so transition coverage, what would be sufficient? Okay. Okay, the same one, A, B, C, D, E, and then A, C, E. Do A still. Good. So you'll notice that here we have one coverage that hits all, one that goes straight through, and what we haven't done is considered all possible combinations of the paths through here. So we haven't considered the fact that, for example, if B is hit, that may disrupt the situation where you go straight through. So we haven't considered, for example, a situation where you have A, B, C, E, and you fail to hit D. For example, maybe B is something which assigns a certain variable to null, and D assigns that variable to something else. But if you go A, B, C, E, it may be bad news. That variable will be uninitialized, or will have a null value in it. So here we haven't considered possible combinations, and hence, oh, now this looks nicer than my diagram. So we have paths here, but we have not done tuples. So with tuple, if we wanted to consider pairs, all possible pairs of incoming and outgoing transitions, let's do those. So I'm going to do transition coverage. Now let's do transition pair coverage. Can anyone give me transition pair coverage for this? So if I wanted paths from start to finish, which are guaranteed for any given node to test out all possible pairs of incoming branches and outgoing branches, what would those be? Give me some test cases for those. cases where we've come in from A directly and we've gone out to E directly in the ACE case. We've covered cases where we came in directly from A to C and then we've gone out to D, right? In this ACDE case. We've also covered cases where we've come into this through B, hence A, B, C, and gone out to E directly, hence the A, B, C, E case. And finally, we've covered the case where we come in this way, so we have A, B, C, and then we have D and E. So these four paths collectively exercise all possible pairs of transitions associated with a node. And here, we could actually formulate this to consider tuples in general, where we go beyond pairs. We start to consider, for example, longer strings where we're not only considering pairs of transitions, but three transitions in a row, for example, and all possible combinations of those. So this is stronger than transition coverage. We're covering additional components as well that might hide a bug. All right? So this is subsumption here. So to go back to our hierarchy here, what we've just talked about is node coverage, state coverage. We've talked about edge coverage, or transition coverage. Edge pair coverage we just talked about. And in fact, that can be extended up to tuples, n tuples. So you have not only pairs of edges leaving, but threesomes of foursomes. Tuples in general, n tuples. Yeah.
Maximum 2 edges per.
That's correct.
Yeah.
I mean, it's not like a given. It's not for a given node. We only have to worry about edges, but in general, we'll have to worry about not just pairs of edges in a row, but three, tuples of length 3, etc. So instead of just having one transition here, consider one here, we'd have 3 combinations, and so we'd be dealing with more nodes fundamentally, or more paths through it. Okay, now if we consider this sort of situation in trying to generalize this to multiple test cases, we can have situations that are problematic with our abstraction. So here we're trying to cover all transitions through this diagram. Okay? So we have an underlying diagram, which we've seen before, and we're trying to get to situations where we've exercised all possible transitions within this diagram. Now, there can be cases where we have can have inconsistencies. So, in this case, for example, this is not particularly easy. Somehow there's it looks like
there's a mystery transition between 5 and 7.
No, there's not. It's just that the actual path has been pulled off in some weird way. So, pardon me. Let me see. Can I edit this thing? I did when I evidently did it on a different computer or something. But fundamentally, this transition from 5 to 7 is actually a going transition and a return one. They're just displaced where the edges are. Similarly, for between 8 and 7, there's a round trip, etc. This diagram attempts to cover all possible transitions here using these colored paths. They describe TC1, TC2, TC3, TC4 here. But there's a problem. There's a problem in terms of the underlying semantics as to whether or not this is in fact possible. Can anyone spot the problem? What was that?
Successful repair.
Oh, there is.
What is the other one?
suggests an underlying issue in the book. I may have to write to the authors. Okay, you're quite right in spotting that, but there's another logical problem also. And it has to do with the annotations. It has to do with the fact we're dealing with an abstraction. So we have to remember, ladies and gentlemen, these are not test cases that we've abstracted. These are paths. Now, what will we need to do in order to really exercise the program is to turn these into specific test cases. We need to formulate cleverly often some particular inputs or some particular situation, scenario that will exercise collectively these test paths. Okay? And that's often harder than it sounds. And in this case, I would argue that you can't do it with this set of test paths. Why not? It has to do with them being abstractions. It has to do with them hiding certain details in terms of just drawing out a set of transitions here. And the information is actually in the underlying annotations here. But you'll notice this transition here is limited to US or EU residents, right? But you'll notice that later on in that same path, you're going this case of unable to repair not US or EU resident. And you're taking that transition there. So here we have a situation where the underlying semantics, as indicated with the annotations, rules out a path that goes through this. And I would actually argue the same situation applies here with these ifs. For example, it may be that if you come in, if you end up, the condition on this guy may be such that, if you go to B here, for example, then you will always go to D in this case. It may be, for example, that the condition on this top if is a more specific version of what's tested later. And essentially, if you go this way, in this case, you're guaranteed to go this corresponding way in this lower case. So in short, while it may seem possible to cover all of these paths for transition pairs, it turns out that certain ones of them are not possible. And you can't cover them. So it may be, for example, that the A, B, C, E case is not logically possible. And this is going to strike us if we come to try to turn these into actual test cases. Because we're going to be trying to cleverly come up with some way to exercise this path, and we'll be unable to do so. Now, in case you think this is purely an academic exercise, I've worked in software teams doing exactly that. So I remember one case specifically with the recalc engine with Excel. Excel automatically recalculates values in a given spreadsheet. When you tweak some of the numbers, it will recalculate automatically. And it turns out it was a fairly involved algorithm to handle all the various cases possible. And the programmer involved ended up doing an analysis much like this to try to get it into cases which would exercise the different paths through the program. They would exercise all of the different transitions within the program. And it's harder than you think, because now you've got to deal with the data dependencies, the fact that certain if statements or certain while statements are undertaken under certain conditions. So coming up with those final set of test cases that exercise your paths will sometimes give you gotchas. And I would argue that that's true not only at the code level, but at the level of broad system functionality as well. So when you're dealing with something like this, for example, for a somewhat larger system, you will discover there's certainly logical cases which would rule out certain paths through the system. You're never going to get a certain path through the system, for example. And you're going to have to consider that when you go to create actual test cases that will fully exercise it. Okay? I would love to see you folks do at least transition coverage on your projects. Love is one way to phrase it. I would be aghast with a capital A if you do not exercise at least state level coverage on your programs. Exercise at least the situation where all of the different user error cases, for example, that can be warned to the user, if those are not exercised by tests, I don't see how you could stand in front of me without a red face and claim that you've tested your program. I would love to see transitions exercised within your system. So all ways you can get from A to B. Maybe it's screens in a web app, pages in a web app. The different ways you can get to this page from other pages, verifying that it works. I would love to see it. I don't ask for anything more than that at the level of sort of high-level testing. I would love to see you use tools like Cobertura or others to gain some confidence that at the statement level or basic block level, you're actually exercising a large part of the functionality of the program. Okay? So I want to see that.
Yeah. So for TPC, it might not always be possible to exercise all the paths, right?
Oh yeah, yeah, that's correct.
Yeah. Okay.
That's correct. So in other words, particularly when you start dealing with these combinations of conditions, it's an abstraction. What you're abstracting over, what is the condition? And this condition that's present here may make it impossible to have certain paths. And that's fine. You just have to realize that the methods don't automatically give that to you. You're going to have to formulate the paths using transition pair reasoning. And then you go back and you ask, okay, can we, is this one actually possible given the nature of what's being tested? And often you'll end up excising some of them. Say, okay, in theory that's possible, but in fact for our cases it's not possible to go this route. So we'll rule it out. Does that make sense?
Yeah. But it will be possible in some way or another using
I think what you're saying is what you're probably asking is, for example, is there a different, could there be a different set of paths that would exercise all transition pairs, but still be legal? In this case, the answer would be no, because transition pairs here are, it's a very tight restriction. But in some of the cases we'll see, the answer is yes. So when we go to the case of prime paths, in fact, there'll be many, there will be situations where you can successfully define a set of prime paths. Let me think about this. I think actually I'm not correct. I think actually even in that case you will be in a situation where you'll just rule things out and say, okay, we can't cover it. What you will be able to do is in some cases formulate test cases that cleverly cover what you need to cover in fewer test cases, for example. And you may discover a particular test case that cannot exercise one of these paths because of the details of the input, and you just have to change that until you can exercise this. But next time we're going to talk about going from something like this. Like this is a HTML encoding algorithm here for encoding. It's in C, and it's encoding HTML strings using an HTML encode like encoding. So if you have a string that involves illegal characters like the @ sign or star or question mark, most importantly, etc. These get encoded in HTML strings as hex values, and this code is designed to do that. And in order to exercise this code, you have to give it strings which contain some of these unusual characters. And you're going to want to force it to get to each possible state here at the least, and hopefully each possible transition to that state. by choosing clever strings to encode. And it's a harder process than you think, but here's an example of specific test cases. It may be that you think you have a string that's going to force it, say, to come this route here, but you actually find that that particular string can't because it'll end up, it has to go this route rather than this one. In which case you need to go back and find a different string that will exercise that particular path. Does that make sense? That you need to cover. Okay, I think I'm just about out of time to let you folks talk with your groups. We will continue on this. So I want honest input from the group here. I could teach a lecture today at 4 o'clock, 4 to 5, and that would be good. I'd be able to finish up this material, go through prime paths, which are a very important part to cover it sort of in one sitting. Alternatively, I could let you work on your projects. So how helpful would it be to work on your projects before class? Give me feedback. To have a group meeting on behalf of the project.
The question to ask is, people going to be
So I just need you. Hands up.
You've got what?
A ton of work to do.
Why?
Not quite great.
We're just putting icing on the cake, actually. I know.
To Travis and I, it would be immensely useful.
Oh yeah, I mean.
Yeah, I guess your part does that little.
Excuse me.
Yes, really well. So it would be useful, yes.
Okay. Okay. We'll use this afternoon then for group work. Okay.
Quit. You can resign the group.
What's that? Can you
I'm going to make my own group.